The James Webb Space Telescope has been in operation for a few years now, and in that time it has done something that nobody fully anticipated. It has not simply confirmed what we expected to find in the early universe. It has returned data that contradicts what our best theory said should be there. And the contradiction is not minor, it is structural. The objects Webb is finding in the oldest regions of the observable universe appear too massive, too complete, and too efficient to have formed in the time the standard model allows them. This is not a marginal anomaly in a fringe publication. It is a genuine scientific tension being discussed in peer-reviewed journals by some of the leading cosmologists alive, including Nobel Prize winners. To understand why this matters, you first need to understand what was expected. Our standard framework for the history and structure of the universe is called the Lambda-CDM model. The name comes from two invisible components that dominate the universe's total energy content. Lambda refers to the cosmological constant, which represents dark energy, the mysterious force responsible for the universe's accelerating expansion. CDM stands for cold, dark matter, a hypothetical form of matter that exerts gravitational influence but does not interact with light. Together, these two components account for roughly 95% of everything. The matter you can touch, the atoms that make up stars and planets and living things, contributes only about 5% of the total. Within this framework, the history of the universe unfolds as follows. Approximately 13.8 billion years ago, everything we can currently observe emerged from an extraordinarily hot, dense state. Space itself expanded rapidly in the event we call the Big Bang. For the first few 100 million years, the universe consisted largely of a hot fog of hydrogen and helium gas. Gravity gradually pulled this gas together. Small structures formed first. Those structures then merged hierarchically into larger ones over hundreds of millions and then billions of years. Galaxies assembled slowly from smaller building blocks. Stars formed inside those galaxies, one generation of stellar explosions seeding the material for the next. The process was gradual, governed by the pace at which matter could collapse, cool, and clump together. This picture was not invented arbitrarily. It was developed over decades and tested against observations from every major telescope humanity has built. And for a long time, it worked. The farther back we looked, the more primitive and sparse the universe appeared to be. The timeline seemed to match the prediction. Webb has been looking further back than any telescope before it. It is reaching epochs when the universe was only a few 100 million years old, when the cosmos was barely 2 to 3% of its current age. And what it finds in that ancient region does not match the prediction. The problem begins with mass. In the very early universe, according to the standard model, there was simply not enough time for gravity to assemble large galaxies. Building a galaxy of substantial mass requires accumulating gas from the surrounding environment, allowing that gas to collapse and cool into stars, losing some of those stars to supernova explosions that cycle material back into the interstellar medium, and then repeating that whole sequence across many millions of years. The early universe did not have millions of years to spare. It had hundreds of millions of years at most before the objects Webb is now observing would need to have already existed in their observed form. And yet, Webb is finding galaxies in that ancient epoch that are comparable in mass to the Milky Way or even larger, not primitive proto-galaxies still assembling themselves from raw gas. Fully formed, densely packed stellar systems. One study published in the Astrophysical Journal reported the detection of 87 candidate galaxies that may have existed only 200 to 400 million years after the Big Bang. The Lambda-CDM model says structures that massive should not have been able to form in that time frame. The numbers simply do not work. The problem becomes sharper when you look at how efficiently these objects formed their stars. In galaxies like our own Milky Way, only about 10% of available gas ever gets converted into stars. The rest remains as diffuse interstellar medium, or gets expelled from star-forming regions by stellar winds and supernova explosions. That 10% efficiency is not just an observed fact about our galaxy. It is a consequence of well-understood physical processes, and it matches the predictions of the Lambda-CDM model. Star formation is a self-limiting process. When gas collapses to form a star, that star immediately begins radiating enormous energy, including ultraviolet radiation that heats and ionizes surrounding gas. Eventually, it ends its life in a supernova explosion that blows gas away from star-forming regions entirely. This feedback is what keeps star formation efficiency low. It is built into our models because it is built into physics. But some of the galaxies Webb has observed in the early universe appear to have converted nearly all of their available gas into stars. Not 10%. Something approaching 100%. Astronomers determine this using spectroscopy, which works by spreading light into its component wavelengths and reading the chemical fingerprints those wavelengths encode. If a galaxy still had substantial gas reserves, that gas would leave its signature in the spectrum. These galaxies do not show that signature. The gas is gone. It became stars at an efficiency that our physical models say should not be possible. A galaxy that formed stars at 100% efficiency would have had to somehow suppress all of that stellar feedback simultaneously across its entire volume at exactly the moment it needed to form. There is no known mechanism for that. No known physics produces that outcome. And yet the spectra suggest it happened. So what are these objects? Astronomers are considering several explanations. None of them are comfortable. The first possibility is that the Lambda-CDM model is simply missing something. Perhaps dark matter behaves differently in the early universe than our models assume. Perhaps physical processes were at work in the early cosmos that we have not yet accounted for. In that case, the observations would be telling us that our theory of structure formation is incomplete and needs to be revised. The second possibility is that these objects are not conventional galaxies at all. Some of them could be dominated by active galactic nuclei, the extraordinarily luminous cores powered by supermassive black holes. If the light from these objects is mostly generated by black hole accretion rather than by stars, they might appear more massive and more luminous than they actually are. But follow-up spectroscopic observations have made this explanation increasingly difficult to sustain for all of the anomalous objects. Some of them really do appear to be built from stars. The third possibility, raised seriously by several physicists, including Nobel laureate Roger Penrose, is that the universe is older than we think. Not slightly older, potentially much older. If the Big Bang was not the actual beginning of the universe, but rather a phase transition in a universe that had already existed for much longer, then the early structures Webb is seeing might not be as impossibly young as they appear. They might have had more time to form because our timeline itself might be wrong. This idea connects to a broader class of cosmological models that challenge the standard Big Bang narrative. Some propose a cyclic universe, one that has gone through many expansions and contractions before our current epoch. Others propose that the Big Bang represented a local or regional event in a universe that has existed in some form for far longer. These are not mainstream positions, but they are being discussed in serious scientific literature, not as settled conclusions, but as possibilities that new data may be forcing scientists to consider. To fully appreciate the significance of what Webb is finding, it helps to understand the extraordinary nature of what it is actually doing when it observes the early universe. When you look at a distant galaxy through any telescope, you are not seeing it as it exists now. You are seeing it as it was when the light you are detecting was emitted. Light travels at just under 300,000 kilometers per second, which sounds impossibly fast until you confront how vast the universe actually is. Light from the moon takes about 1.25 seconds to reach us. Light from the sun takes about 8 minutes. Light from the nearest star beyond our own takes about 4 years. The galaxies? Webb studies are billions of light years away. When Webb observes a galaxy that existed only 300 million years after the Big Bang, It is detecting light that has been traveling for approximately 13.5 billion years. It is not seeing a galaxy as it exists today. It is seeing a fossil, a snapshot of a universe that no longer exists, preserved in ancient photons that have been crossing expanding space for virtually the entire history of the cosmos. The expansion of space adds an additional complication. Because space itself has been stretching during all the time that light has been traveling, the light arrives redshifted. Its wavelength has been stretched toward the red end of the electromagnetic spectrum. The amount of redshift tells you how much space expanded during the photon's journey. From that, astronomers can calculate how far away the source was when the light was emitted and how long ago that emission occurred. It is one of the most elegant tools in observational astronomy. One of the most distant galaxies Webb has confirmed, designated JWST, has a redshift that places it approximately 13.5 billion light-years from Earth in look-back time. When its light was emitted, the universe was only about 290 million years old. That is an almost incomprehensibly short time after the Big Bang for a fully formed galaxy to exist. And yet, there it is, recorded in Webb's infrared detectors. That galaxy is not sitting still. The universe has continued expanding in the 13.5 billion years since the light we observe was emitted. Today, JWST is estimated to be more than 30 billion light-years away from us, well beyond the edge of what we can ever observe. Any light it emits now will never reach us. Space is expanding between us and it faster than light can cross the growing distance. Whatever that galaxy has become over the past 13 billion years, we will never know. We are left with a single ancient snapshot, and that snapshot alone is already telling us something that our models cannot fully explain. This brings us to one of the most counterintuitive features of modern cosmology. The observable universe is not the whole universe. The observable universe is simply the region from which light has had time to reach us since the beginning of our cosmic epoch. It forms a sphere roughly 92 billion light-years across, centered on wherever you happen to be observing from. Beyond that edge, space continues. Galaxies exist. Stars burn. But their light will never reach us because the universe is expanding faster than it can travel. As you look toward the boundary of the observable universe, you are also looking further and further back in time until you reach the cosmic microwave background radiation. This is the faint afterglow of the moment the universe became transparent to light, approximately 380,000 years after the Big Bang. Before that moment, the early universe was too hot and dense for light to travel freely. The cosmic microwave background is the oldest light we will ever detect. It fills the entire sky at a nearly uniform temperature of about 2.7 degrees Kelvin, just above absolute zero, but tiny temperature fluctuations in the pattern, on the order of 1 part in 100,000, reveal the seeds of the large-scale structure that would eventually form galaxies, galaxy clusters, and the vast cosmic web we see today. Those fluctuations have been mapped in exquisite detail by missions including the Wilkinson Microwave Anisotropy Probe and the Planck satellite. The patterns match the predictions of the Lambda-CDM model extremely well. This is part of what makes Webb's observations so scientifically significant. On the largest scales, the Lambda-CDM model works beautifully. The cosmic microwave background matches it. The distribution of galaxies across billions of light-years matches it. But on the scale of individual early galaxies, something appears to go wrong. The model predicts that early galaxies should be small, dim, and still assembling themselves from raw material. Webb is finding bright, massive, fully formed systems. Astronomers have been careful to distinguish between confirmed findings and candidate findings. This distinction matters enormously. Some of the most extreme early galaxy candidates need additional follow-up observations before their redshifts can be confirmed with certainty. A galaxy that appears to be at a certain redshift based on its color can sometimes turn out to be a different type of object at a closer distance, masquerading as something far more ancient but spectroscopic conformation, which involves measuring the actual wavelength shifts of specific spectral lines rather than inferring redshift from color alone, is the gold standard. And Webb's NIR-SPEC instrument has been conducting spectroscopic follow-ups on many of its candidate early galaxies. In most cases, the high redshift identifications have held up. The galaxies are really there. They are really as distant as they appear. The tension with theory is not an artifact of measurement error. It is a genuine feature of the early universe. One proposal for resolving this tension without abandoning the Lambda-CDM model involves adjusting the properties of dark matter. In the standard model, dark matter is cold, meaning its particles were moving slowly relative to the speed of light when the universe was young. This has important consequences for how structure forms. Cold, dark matter tends to clump into small halos first, which then merge hierarchically into larger ones. This bottom-up pattern of structure formation is one of the key predictions of the CDM framework. Some researchers have proposed warm dark matter instead, whose particles were moving faster in the early universe. Warm dark matter would suppress the formation of very small structures, but might allow certain intermediate structures to form differently. However, warm dark matter models generally predict fewer small galaxies than we observe in the local universe, which creates a different set of problems. There is no version of dark matter physics that neatly resolves all observations simultaneously. Every proposed modification fixes something but breaks something else. Another proposal involves modifying our understanding of star formation itself. Perhaps in the early universe, conditions were so different that the feedback mechanisms that limit star formation efficiency today were weaker or less effective. The first generation of stars, known as population 3 stars, formed in clouds of pristine hydrogen and helium without any heavier elements. These stars were likely far more massive than typical stars today and would have ended their lives in titanic explosions that rapidly enriched the surrounding gas with heavy elements. Perhaps the dynamics of star formation in that primordial environment briefly allowed higher efficiencies before feedback mechanisms caught up. This idea has some theoretical support. In simulations of the very early universe, before the first generation of supernovae had enriched the surrounding gas, star formation could in principle proceed somewhat more efficiently. But simulations struggle to reach the near 100% efficiencies that some Webb observations appear to require. The gap between theoretical maximum and observed reality remains uncomfortably wide. A more radical proposal involves the possibility that the gravitational constant itself was temporarily stronger in the early universe than it is today. A stronger gravitational force would pull gas together faster, allow more rapid cooling, and enable star formation to proceed more quickly and completely than current physical laws would allow. Some scalar field theories and modified gravity frameworks predict exactly this kind of time-varying gravitational strength, but there is no direct evidence that gravity has changed its strength over cosmic history, and testing such ideas is extraordinarily difficult. Perhaps the most philosophically significant possibility is that the Big Bang was not the beginning of the universe, or at least not the kind of beginning we usually imagine. Our standard picture of the Big Bang involves the entire observable universe emerging from an infinitely or near infinitely hot, dense state called a singularity. But here is the crucial detail. Our physical theories break down at that singularity. General relativity, our best theory of gravity and space-time, predicts the singularity but cannot describe what happens at it. Quantum mechanics, which governs matter at the smallest scales, is not properly integrated with general relativity at the energy scales relevant to the earliest moments of the universe. A complete theory of quantum gravity, something physicists have been pursuing for decades, does not yet exist. In the absence of that complete theory, we cannot say with certainty that the universe had an absolute beginning. There are serious proposals in theoretical physics in which what we call the Big Bang was not a creation event, but a transition. Quantum cosmologists have proposed that the universe could have tunneled into existence from a prior quantum state, or that it underwent a bounce from a previous contracting phase, or that our universe is one pocket in a vast, eternally expanding multiverse in which Big Bang events occur continuously in different regions. Roger Penrose, who shared the Nobel Prize in Physics in 2020 for his work on black holes and general relativity, has proposed a model called conformal cyclic cosmology. In this framework, our universe is one in an infinite sequence of aeons. At the end of each aeon, when all massive particles have decayed and only massless radiation remains, the universe loses its sense of scale, and a new Big Bang becomes the start of the next cycle. Penrose has argued that this model might be testable through specific patterns imprinted in the cosmic microwave background. The search for those patterns is ongoing. Webb is unlikely to directly test ideas like conformal cyclic cosmology. What it can do, and is doing, is provide increasingly detailed maps of structure in the early universe. Maps that any viable cosmological theory must be able to reproduce. If the Lambda-CDM model cannot match those maps, it needs to be modified or replaced. If a replacement model can match both the early universe observations and everything else we have measured, it earns serious consideration. This is how science is supposed to work. The history of cosmology includes exactly this kind of productive tension. In the late 1990s, astronomers studying a class of stellar explosions called Type Ia supernovae discovered that the expansion of the universe was accelerating, not slowing down as gravity should have caused. This was profoundly unexpected. Initially, it was deeply controversial, but the evidence was solid and cosmologists had to account for it. The result was the introduction of dark energy into the Lambda-CDM model, a placeholder for whatever force is driving the acceleration. The discovery earned the Nobel Prize in Physics in 2011. Dark energy remains mysterious to this day, but its existence is now standard cosmological fact. Webb's observations may be the beginning of a similarly transformative moment. We do not know yet. The anomalies are real, but their resolution is not clear. Are they telling us that dark matter behaves differently than we assumed? That star formation in the early universe operated by different rules? That the universe is older than 13.8 billion years? That something entirely new is at work? All of these possibilities are being actively investigated. The universe's process of galaxy formation is intimately tied to the formation of dark matter halos. In the Lambda-CDM model, dark matter forms roughly spherical concentrations held together by gravity. These halos form hierarchically, small halos first, then larger halos through mergers. Ordinary matter, the gas that will eventually become stars, falls into these dark matter potential wells, cools, and fragments into stellar populations. The visible portion of a galaxy, its stars, its gas, and its dust, forms within and around one of these dark matter halos. The rate at which halos of different masses form at different epochs in cosmic history is calculable from first principles within Lambda-CDM, and it is precisely this calculation that Webb's observations are challenging. When astronomers catalogue the galaxies Webb finds at a given epoch and compare the distribution of their masses to what Lambda-CDM predicts should exist in corresponding dark matter halos, the observed number of massive early galaxies exceeds the theoretical prediction by substantial factors. For the most extreme examples, the discrepancy reaches factors of 10 or more. One way to resolve this would be to increase the efficiency with which ordinary matter is converted into stars within these early halos. But as we have already discussed, that efficiency has physical limits imposed by stellar feedback, and some early galaxies appear to be approaching or exceeding those limits. Another way would be to invoke a different formation channel entirely. Perhaps some of the most extreme early objects are not conventional galaxies, but rather massive black holes surrounded by luminous accretion disks, objects we call quasars. Webb has found quasars at earlier cosmic times than ever before, and some of the most massive ones pose their own puzzle. How did supermassive black holes grow to masses of billions of solar masses when the universe was only a few 100 million years old? The growth of black holes through accretion is constrained by a physical limit called the Eddington limit. When a black hole accretes matter, the radiation pressure from the hot, infalling gas pushes outward. At the Eddington limit, radiation pressure balances gravity and accretion cannot proceed faster. For a black hole to grow from a stellar seed to a supermassive black hole in only a few 100 million years requires either temporary super-Eddington accretion, extremely massive initial seeds, or both. Webb has found early quasars powered by black holes with masses of hundreds of millions to billions of solar masses at epochs when the universe was less than 1 billion years old. Explaining how these black holes grew so fast is itself a significant open problem in astrophysics. This question of early supermassive black holes connects to a broader puzzle about how galaxies and their central black holes co-evolve. We know that in the present-day universe, the mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's central stellar component. This correlation holds across many orders of magnitude of galaxy mass, suggesting that galaxy growth and black hole growth are deeply linked processes that regulate each other through feedback. Radiation and jets from the active black hole heat and expel gas from the galaxy, slowing star formation. Meanwhile, star formation and gas accretion feed both the galaxy's stellar mass and the black hole's mass. But in the very early universe, this coevolution appears to follow a different pattern. Some early galaxies have very massive black holes relative to their total stellar mass, suggesting the black hole grew faster than the stars. Others appear to have built up stellar mass rapidly without an obviously dominant central black hole. Webb is mapping how the correlations between black hole mass and galaxy mass evolve across cosmic time, and the picture emerging is more complicated than the clean correlations of the nearby universe suggest. The present-day regularities may be the end product of a far more chaotic early history than we appreciated. The question of first light is deeply connected to all of this. First light refers to the moment when the first stars in the universe ignited, ending what cosmologists call the cosmic dark ages. Before first light, the universe was filled with neutral hydrogen gas that absorbed ultraviolet radiation, making it opaque to that portion of the electromagnetic spectrum. The cosmic dark ages lasted from roughly 380,000 years after the Big Bang, when the cosmic microwave background was released, to somewhere between 100 million and 800 million years after the Big Bang, when the first stars and galaxies produced enough ultraviolet radiation to reionize the surrounding hydrogen. This process is called reionization. It marks the transition from the dark universe of the early cosmos to the universe we recognize today, illuminated by galaxies and quasars. The massive early galaxies Webb has found in this epoch were likely major contributors to reionization. Their ultraviolet photon output would have helped ionize the surrounding hydrogen, gradually clearing the cosmic fog. But here again, the details are puzzling. If the early galaxies were producing stars as rapidly and efficiently as Webb's observations suggest, the reionization timeline may need to be revised. Models calibrated to the standard Lambda-CDM galaxy formation history may need updating. There is also the question of metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. All such heavy elements were produced inside stars through nuclear fusion and supernova explosions. The very first stars, population 3 stars, formed from gas containing no metals at all. When those stars died, they enriched the surrounding gas with metals, which went into subsequent generations of stars. The metallicity of a galaxy is therefore a record of its star formation history. A galaxy that has gone through many generations of stars will have higher metallicity. Spectroscopic observations by Webb can measure the metallicities of early galaxies, providing an independent check on their star formation histories. Early results are intriguing. Some early galaxies have lower metallicities, consistent with being young and less chemically evolved. But others have surprisingly elevated metallicities for their apparent age, suggesting they have already processed significant amounts of gas through multiple stellar generations. This is another line of evidence suggesting that star formation in the early universe was proceeding faster than standard models predict. Some theoretical proposals have attempted to address Webb's observations by invoking a top-heavy initial mass function for early stars. The initial mass function describes the distribution of stellar masses produced in a given star-forming event. In nearby star-forming regions, many low-mass stars are formed for every high-mass star. If the early universe produced proportionally more massive stars than today, the overall luminosity and stellar feedback characteristics of early galaxies would be different. Massive stars are brighter and shorter-lived than low-mass stars. A top-heavy initial mass function would produce galaxies that appear brighter per unit of stellar mass, which could partially account for the anomalously high luminosities Webb is finding. But it would also produce different chemical enrichment patterns. And it is not clear that all of the observations can be simultaneously explained in this way. The early galaxy observations also intersect with another significant unsolved problem in modern cosmology: the Hubble tension. The Hubble constant describes how fast the universe is expanding today. It is measured in units that describe the recession velocity of galaxies per unit of distance. Knowing the Hubble constant precisely is important for calculating the age and size of the observable universe and for testing cosmological models. The problem is that the two primary methods for measuring it give different answers. The first method uses the cosmic microwave background. By analyzing the detailed pattern of temperature fluctuations within the Lambda-CDM framework, cosmologists can infer the Hubble constant with high precision. The Planck satellite measurement gives a value of about 67 kilometers per second per megaparsec. The second method uses a chain of distance measurements in the local universe called the cosmic distance ladder. Astronomers measure distances to nearby stars using parallax, use those distances to calibrate variable stars called Cepheids, use Cepheids to calibrate the peak luminosities of type Ia supernovae in nearby galaxies, and then use those supernovae in distant galaxies to measure the expansion rate directly. This chain gives a value of about 73 kilometers per second per megaparsec. That gap between 67 and 73 sounds small in percentage terms, about 9%. But both measurements claim statistical uncertainties of only 1 to 2%. The discrepancy is therefore statistically significant, reaching about 5 standard deviations, well above the threshold conventionally required to declare a discovery in physics. And it has persisted for years, despite careful checks and independent verifications by multiple teams using different methods. The Hubble tension is not explained by any known systematic error in either measurement. Some researchers have proposed that the Hubble tension and the early galaxy problem are related, that both anomalies point toward the same underlying modification of the standard model. If the early universe was different from what Lambda-CDM assumes, that could affect both the apparent Hubble constant inferred from the microwave background and the rate of structure formation that produced early galaxies. The connection is not yet well established, but the possibility is being actively explored. What makes this scientific moment so striking is not any single anomaly, is the accumulation of anomalies. Several independent lines of evidence, all pointing in the same direction, all suggesting that our standard cosmological model is incomplete. The early galaxy excess, the Hubble tension, the persistence of dark matter and dark energy as unexplained ingredients, the inability of particle physics theories to predict the value of the cosmological constant to within many orders of magnitude. These may not be separate problems with separate causes. They may be symptoms of a single deeper misunderstanding that we have not yet identified. Identifying what that misunderstanding is would be one of the greatest scientific achievements in history. It would mean discovering something fundamental about the nature of space, time, matter, and energy that has been hidden from our previous observations. and the clues provided by Webb by the cosmic microwave background, by gravitational lensing surveys, and by the expanding toolkit of observational and theoretical cosmology are pointing the way. To understand why Webb can see what no telescope before it could, it helps to think about what it is actually detecting. All telescopes collect light, but light comes in many forms. Human eyes detect visible light, the narrow band of the electromagnetic spectrum between roughly 400 and 700 nanometers in wavelength. This visible window was the primary domain of astronomical telescopes from Galileo's 17th century instruments through the great reflecting telescopes of the 20th century. But the universe emits radiation across the entire electromagnetic spectrum, from high-energy gamma rays and X-rays through ultraviolet light, through visible light, through infrared radiation, through microwaves and down to radio. Webb was designed specifically for the near-infrared and mid-infrared portions of the spectrum, covering wavelengths from about 0.6 micrometers, barely into visible red light, to 28.5 micrometers, deep into the thermal infrared. This range was chosen for a specific reason related to the redshifting of distant galaxies. When light travels through expanding space, its wavelength stretches proportionally to how much space has expanded during its journey. A photon emitted in the ultraviolet range from a galaxy that existed when the universe was only 300 million years old reaches us with its wavelength stretched by a factor of roughly 10 to 15. That ultraviolet photon arrives as an infrared photon. To see the most distant and earliest galaxies, you need an infrared telescope. The Hubble Space Telescope had some infrared capability, but its mirror was only 2.4 meters across, and its infrared detectors were limited by the telescope's operating temperature. Hubble runs relatively warm, which means the telescope itself emits thermal infrared radiation that overwhelms faint signals from distant galaxies. Webb's mirror is 6.5 meters in diameter, giving it more than 6 times the light-collecting area of Hubble in the relevant wavelength ranges, and Webb operates at a temperature below 50 Kelvin, approximately negative 223 degrees Celsius, cold enough that its own thermal emission is negligible compared to the astronomical signals it is trying to detect, achieving. And maintaining this temperature requires a large 5-layer sunshield, roughly the size of a tennis court, which keeps the telescope perpetually in the shadow of both the Sun and the Earth simultaneously. The sunshield is one of the most complex engineering elements ever deployed in space. Webb orbits the Sun at a distance of about 1.5 million kilometers from Earth, at a gravitational balance point called the second Lagrange point, or L2, where the combined gravitational forces of the Sun and Earth allow a relatively stable orbit while keeping the telescope thermally shielded. This location places Webb far outside Earth's radiation belts and thermally isolated in a way that no Earth-orbiting observatory can achieve. Webb's primary instruments work in concert to provide capabilities that are qualitatively different from anything that existed before. The near-infrared camera captures images across wavelengths from about 0.6 to 5 micrometers. This is the instrument responsible for most of Webb's iconic deep-field images, including the first full-color image released in July of 2022, which showed thousands of galaxies in a tiny patch of sky that would appear mostly empty through a smaller telescope. The near-infrared spectrograph can simultaneously capture spectrums from 5 to 28.5 micrometers and enables both imaging and spectroscopy at these longer wavelengths. It is particularly sensitive to thermal emission from dust and allows Webb to study the dust-obscured star formation that optical and near-infrared observations would miss entirely. Many star-forming galaxies are enshrouded in dust that absorbs ultraviolet and visible light and re-emits it as infrared radiation. Understanding dust-obscured star formation is essential for a complete census of the universe's star formation history. Several surveys using the mid-infrared Instruments have found a significant population of dust-enshrouded early galaxies that were completely invisible to previous surveys. These galaxies were faint or invisible in visible and ultraviolet light, but clearly revealed by their mid-infrared emission. Including them in the census of early galaxies makes the early universe's star formation rate look even higher than the most anomalous near-infrared observations had suggested. When you add dust-obscured galaxies to the count of already anomalously massive early galaxies, the picture becomes more challenging for the standard model, not less. The deep field images Webb has captured in its first few years of operation have already generated thousands of scientific publications. Each image is a multi-dimensional dataset containing not just the positions and brightnesses of objects, but color information that encodes redshift, spectral information that reveals chemical composition and dynamics, and temporal information when the same fields are observed repeatedly to detect variability. From these datasets, astronomers are assembling a picture of the early universe with more detail and more anomalies than any model anticipated. The anomalies are not confined to galaxy masses and star formation efficiencies. They include the sizes of early galaxies, which appear to have been more compact than expected and then grew larger over time through mergers. They include the colors of early galaxies, which sometimes indicate older stellar populations than should have had time to form. And they include the shapes of early galaxies, which are often irregular and disturbed, suggesting frequent mergers in a denser early universe, but also sometimes surprisingly disk-like or spiral-like at epochs when models do not predict such regular structures should yet exist. The question of early disk galaxies is particularly interesting. In the Lambda-CDM model, galaxy mergers are expected to be extremely common in the early universe when galaxies were packed more closely together. Mergers are violent, disruptive events that tend to destroy ordered disk structures and create irregular or elliptical galaxies. A galaxy can rebuild a disk over time after a merger, but this takes billions of years. Finding thin, stable disk galaxies in the very early universe, when mergers should have been ubiquitous, is another puzzle. Webb has found what appear to be disk galaxies at redshifts corresponding to less than 1 billion years after the Big Bang. If confirmed, these findings suggest that either mergers were less disruptive in the early universe than models predict, or that disk rebuilding was much faster than we understand, or that some early galaxies avoided the merger-dominated environment that the standard model predicts. Each of these possibilities has implications for our understanding of galaxy formation physics, and none of them fits neatly into the existing framework. There is also an important connection between early galaxy formation and the distribution of heavy elements in the universe today, a connection that ultimately touches the question of life itself. Every atom of carbon, oxygen, nitrogen, silicon, and iron that exists today was made inside a star and dispersed by that star's death. The atoms in your body were forged in stars that lived and died before the sun was born. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was processed through at least one stellar generation before it found its way into the nebula from which the solar system formed about 4.5 billion years ago. The history of chemical enrichment begins with those population 3 stars made of pure hydrogen and helium. When they died, they scattered carbon and oxygen and heavier elements into the surrounding gas for the first time. Second-generation stars formed from this enriched gas lived longer, and when they died, added more heavy elements. Generation after generation, the cosmic chemical composition has grown richer and more capable of supporting the chemistry of life. This story of chemical evolution is partially recorded in the spectra of distant galaxies. Webb can measure the abundance of elements like oxygen and hydrogen in early galaxies using specific emission lines, revealing how chemically evolved those galaxies were at the time their light was emitted. Early results show that some early galaxies were already significantly enriched in heavy elements within the first billion years after the Big Bang. consistent with having gone through multiple generations of star formation quickly. This rapid enrichment is another piece of evidence that star formation in the early universe proceeded faster and more completely than standard models predict. One of the fundamental questions in astrobiology, the study of the origin and distribution of life in the universe, is how common planets capable of supporting life are. Answering that question requires knowing how quickly heavy elements were dispersed throughout the cosmos. Because life as we understand it requires carbon, oxygen, and other heavy elements that only stars can produce, the timeline of chemical enrichment directly constrains the timeline of habitability. If star formation and chemical enrichment in the early universe were faster and more efficient than we thought, heavy elements may have been available throughout the universe at earlier cosmic times than current models assume. This could mean that rocky planets with the chemical ingredients for life were forming earlier in cosmic history than we have assumed. Some researchers have speculated that life could have first emerged in the universe not on planets around stars born 10 billion years ago, but potentially even earlier. Webb's observations, by pushing back the timeline of chemical enrichment, indirectly inform this possibility. To understand the full depth of what Webb is confronting, it helps to appreciate the intellectual history, how humans arrived at the idea that the universe had a beginning at all. For most of human history, the cosmos was assumed to be eternal and unchanging. The stars had always been there. The heavens were the very definition of permanence. When Isaac Newton published his laws of gravity in 1687, he struggled with an obvious implication. If gravity is universal and attractive, why has the entire universe not collapsed inward on itself? His answer was essentially theological. God must be occasionally correcting the perturbations that would otherwise cause collapse. Newton's universe was static, infinite, and maintained by divine intervention. It was Albert Einstein who first put the mathematics of a dynamic universe within reach, and ironically, he used that mathematics to preserve the idea of a static cosmos. When Einstein completed his general theory of relativity in 1915, he applied it to the universe as a whole. His equations, like Newton's, implied that a universe filled with matter should either be expanding or contracting. A static universe was unstable. To prevent this, Einstein introduced a term he called the cosmological constant, a kind of repulsive energy built into the fabric of space-time that would counterbalance gravity and allow a static universe to remain stable, he later called. This is greatest blunder. The reason he called it a blunder was that within a decade, the universe was discovered to be expanding after all. Edwin Hubble, working with telescopes at the Mount Wilson Observatory in California, showed in 1929 that distant galaxies are moving away from us and that galaxies farther away are receding faster. The relationship between distance and recession velocity is now called Hubble's law. Its existence implies that the universe was once much smaller and denser than it is today, and that if you ran time backward, everything converged toward a single state of extreme density and temperature. Georges Lemaitre, a Belgian priest and physicist, had actually proposed this idea independently in 1927. Lemaitre called it the hypothesis of the primeval atom. Einstein initially rejected it, reportedly telling Lemaitre that while his mathematics was correct, his physics was abominable. After Hubble's observations, Einstein changed his view. The static universe was gone. The expanding universe had won. The term Big Bang itself was coined derisively. Fred Hoyle, a brilliant British astrophysicist who advocated for an alternative steady-state theory of the universe, used the phrase mockingly in a 1949 radio broadcast, intending it to sound ridiculous. The name stuck. Hoyle's steady-state theory did not the discovery of the cosmic microwave background. Radiation in 1965 by radio. Astronomers Arno Penzias and Robert Wilson provided the decisive observational confirmation that the universe had been hot and dense in the past. The Big Bang became established fact. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. The Planck satellite, which completed its observations in 2013 and released final results in 2018, measured the temperature fluctuations in the cosmic microwave background to extraordinary precision. The Lambda-CDM model's predictions matched to better than 1% for most parameters. This is what makes the Webb anomalies so striking. The Lambda-CDM model doesn't just fit the microwave background, it fits the abundance of light elements produced in the first few minutes after the Big Bang. It fits the distribution of galaxies across hundreds of millions of light years. It fits the large-scale clustering of matter. It fits the accelerating expansion driven by dark energy. All of it fits within a coherent framework. And then there are the early galaxies Webb is finding, and they don't fit. The tension is described in the cosmological literature using specific terminology. When a specific observation contradicts a model's prediction, it is called a tension if the discrepancy is statistically significant but not yet definitive. It is called a crisis if the evidence becomes overwhelming. Right now, the Webb early galaxy observations are generating what many researchers describe as a significant tension, not yet a crisis, but heading in that direction if new data continues to accumulate in the same direction. The standard cosmological model is, at its core, a framework built substantially on things we do not understand. 5% ordinary matter, 27% unknown dark matter, 68% unknown dark energy. And now Webb is telling us that even the ordinary matter we do understand does not behave in the early universe the way our models predict. This situation is either deeply uncomfortable or tremendously exciting, depending on your perspective. For a scientist, it is exciting. It means the universe still has fundamental secrets. It means our best theories are provisional, as all scientific theories are, and that better theories are waiting to be found. What might those better theories look like? One serious alternative to Lambda-CDM is a class of models called modified gravity. In these frameworks, Einstein's general relativity is modified at large scales. The most well-known version is called modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983. MOND modifies the law of gravity at very low accelerations, specifically the regime that applies at the outskirts of galaxies. In this regime, MOND predicts galaxy rotation curves without requiring any dark matter, and it does so remarkably well across many orders of magnitude of galaxy size and brightness. But MOND has significant problems at larger scales. It does not naturally explain the behavior of galaxy clusters, the cosmic microwave background fluctuations, or the large-scale structure of the universe. Various relativistic extensions of MOND have been developed, but none has achieved the broad explanatory success of Lambda-CDM. Some researchers have proposed that dark energy is not a constant, but a field that evolves over time, sometimes called quintessence. Others have proposed modifications to the inflationary epoch, the period of extremely rapid expansion thought to have occurred in the first tiny fraction of a second after the bigger bang. Inflation was proposed by Alan Guth in 1980 to solve several puzzles about the early universe. Why is the cosmic microwave background so uniform across regions of space that should not have been in causal contact? Why is the universe so close to geometrically flat? Inflation solves these problems by postulating that the very early universe went through a phase of exponential expansion driven by a hypothetical field called the inflaton. This expansion was so rapid that a tiny causally connected region was stretched to a scale much larger than what we can observe today, erasing initial irregularities and imprinting the quantum fluctuations that seeded all subsequent structure. The connection to Webb's observations is indirect but real. Different inflationary models predict slightly different initial conditions for the distribution of matter. Different initial conditions lead to different predictions for how structure forms, which eventually affects what kinds of galaxies form and when. If Webb's observations eventually force a significant revision of structure formation models, those revised models may require a different version of inflation or a different mechanism altogether for generating the initial perturbations. This is the kind of cascading effect that fundamental discoveries in cosmology can have. A puzzle about galaxy masses in the early universe, potentially, ripples back to questions about the first fraction of a second after the Big Bang and forward to questions about the ultimate fate of the cosmos. The ultimate fate of the universe depends on what dark energy turns out to be. If it is truly a cosmological constant unchanged over time, the universe will expand forever at an accelerating rate. Galaxies beyond our local group will eventually recede beyond our observable horizon. In the far future, stars will exhaust their fuel. Black holes will slowly evaporate by emitting Hawking radiation. The universe will approach a state of maximum entropy called the heat death. If dark energy grows stronger over time, it could eventually tear apart not just galaxies and clusters, but individual atoms in an event called the Big Rip. If it weakens and reverses, gravity might eventually halt the expansion and cause the universe to recollapse in a big crunch. Future observatories, including the Euclid Space Telescope and the Vera Rubin Observatory, are measuring the expansion history of the universe in far more detail, potentially revealing whether dark energy has changed over time. Every piece of this story connects to every other piece. The nature of dark energy connects to the ultimate fate of the universe. The nature of dark matter connects to how galaxies form. The physics of inflation connects to the initial conditions that determined all subsequent structure. And sitting at the intersection of all of these questions is the James Webb Space Telescope, sending back data that complicates and enriches our understanding at every frontier. The development of Webb itself illustrates how deeply collaborative modern science has become. The telescope was designed and built by an international collaboration involving NASA, the European Space Agency, and the Canadian Space Agency. Engineers and scientists from more than a dozen countries contributed. The mirror segments were made from beryllium and coated with a thin layer of gold, chosen for its exceptional reflectivity in the infrared. The detectors were developed specifically for Webb's requirements, pushing the state-of-the-art in infrared sensor technology. The microshutter arrays in the spectrograph, those tiny individually controllable shutters, were a novel invention created specifically for Webb's needs. The entire project cost approximately $10 billion over its multi-decade development timeline, making it one of the most expensive scientific instruments ever built. The cost is often cited by critics who question whether such investments in pure science are justified. The history of science suggests they are, and not just because of the direct scientific knowledge gained. Technologies developed for scientific instruments frequently find applications in medicine, communications, and manufacturing. But even setting aside practical applications, there is a case that understanding the universe is intrinsically valuable. That knowing where we came from and how the cosmos works is worth pursuing regardless of immediate practical benefit. This argument has driven human inquiry since antiquity. The curiosity that motivates cosmology is the same. Curiosity that motivates all of science. The coming decades in observational cosmology are likely to be among the most scientifically productive in the history of the discipline. Webb has opened a new window on the early universe. The square-kilometre array, currently under construction in South Africa and Australia, is designed partly to observe the radio emission from neutral hydrogen across a wide range of redshifts, potentially mapping the structure of the universe through the epoch of reionization and into the cosmic dark ages. Combined with Webb's observations of the earliest galaxies, the square-kilometre array will help fill in the missing chapter of cosmic history between the microwave background and the first structures we can currently see. Gravitational wave detectors, including LIGO, Virgo, and the future space-based LISA Observatory, will open a gravitational wave window on some of the most energetic events in cosmic history, including the mergers of supermassive black holes and the possible detection of a gravitational wave background from the early universe. Next-generation cosmic microwave background experiments will measure the faint polarization patterns that might reveal the signature of inflationary gravitational waves. Each of these observational windows provides different and complementary information about the universe's history and structure. Combining them, a process called multi-messenger astronomy has already proven extraordinarily powerful. Extremely large ground-based telescopes with primary mirrors 30 meters or more in diameter are also coming online. These instruments will be able to perform spectroscopy on faint early galaxies that even Webb can only barely detect, providing even more precise measurements of the properties of the earliest cosmic structures. As these new observations accumulate and are compared with increasingly sophisticated models, the picture of cosmic history will sharpen. The anomalies will either deepen into a genuine crisis that forces fundamental revisions of our understanding, or they will resolve into refinements that teach us more about the details of known physics operating in extreme early conditions. Either way, what we learn will be foundational. It will shape how we understand dark matter and dark energy, how we model the formation of stars and galaxies, how we trace the chemical evolution that ultimately made life possible, and how we think about the beginning and future of the universe itself. There are few more intellectually exciting places to be right now than at the intersection of observational cosmology and fundamental physics, watching Webb's data accumulate and waiting to see what the universe reveals about its own beginning. We have always looked at the sky and wondered, what is it? How did it form? Are we alone in it? The questions have not changed much over the millennia, but our ability to pursue them has been transformed beyond recognition. James Webb is our current most powerful instrument for chasing those answers. And the answers it is revealing, incomplete and puzzling as they are already changing how we think about the universe's beginning. What we can say with confidence is that the early universe is not what the standard model predicted. The structures that formed in those first few 100 million years are bigger, brighter, and more numerous than expected. The star formation efficiency in those structures appears to exceed what known physics easily allows. The chemical enrichment happened faster than models anticipated. The supermassive black holes grew more quickly than the Eddington limit comfortably permits. And the whole picture, taken together, is coherently anomalous in a way that is increasingly difficult to dismiss. What comes next in both observation and theory will build on what Webb has shown us. And what Webb has shown us is that the early universe is not what we thought. That is not a failure. It is an invitation to understand better. And understanding better, one discovery at a time, is what science has always been. If this kind of question interests you, consider subscribing so you don't miss the next piece of the story as it unfolds. The universe is still talking. We are only just beginning to learn the language. To truly grasp the magnitude of what is being contested here, we need to sit with the numbers a little longer. The Lambda-CDM model is not a rough guess. It is a framework that has survived decades of extraordinarily precise testing. Its predictions about the abundance of helium and deuterium produced in the first few minutes after the Big Bang, a process called Big Bang nucleosynthesis, match measurements from some of the most ancient stars we can observe to better than 1%. Its predictions about the acoustic peaks in the cosmic microwave background, the specific pattern of temperature fluctuations across the sky, matched the Planck satellite data with breathtaking precision. Its predictions about how galaxies cluster together on scales of hundreds of millions of light-years, as measured by enormous surveys that have mapped millions of galaxies, agree with observations within the expected statistical uncertainties. This is not a model that wobbles. It is a model that has earned its place through repeated confrontation with data across wildly different physical scales and epochs. And yet Webb is showing us something it cannot accommodate. The significance of this should not be understated, because science does not produce crises lightly. When a well-tested model fails to match observation, the first response of scientists is always to suspect the observation. Could there be a systematic error in the measurement? Could the data analysis pipeline have introduced a bias? Could the instruments be producing artifacts that mimic the signal? These are not cynical responses. They are rational ones, grounded in the understanding that measuring light from objects that are billions of light years away and billions of years old is extraordinarily difficult, and that errors in such measurements are far more likely than errors in a framework confirmed across so many independent tests. So astronomers have been checking their work. They have cross-checked photometric redshifts against spectroscopic redshifts. They have compared data from different instruments on Webb. They have reanalyzed the same fields using different reduction pipelines. They have compared Webb's findings against what Hubble and Spitzer detected in the same regions of sky, checking for consistency. They have examined whether contamination from nearby objects might be inflating apparent luminosities. And the answer, so far, is that the anomalies survive these checks. The galaxies that appear too massive and too complete in the early universe keep appearing too massive and too complete when the analysis is redone more carefully. This is what elevates the issue from a measurement question to a theoretical one. The anomalies appear to be real features of the universe, not artifacts of our instruments or our methods. This leaves theorists in an uncomfortable but ultimately exhilarating position. They must either find a way to make the Lambda-CDM model produce these early massive galaxies without abandoning the model's other successes, or they must be open to the possibility that the model needs to be substantially revised. Neither path is easy. The challenge of modifying Lambda-CDM without breaking it can be illustrated through one of the most actively debated proposals: the idea that the primordial power spectrum of density fluctuations was enhanced on certain scales. In the standard model, inflation produces a nearly scale-invariant spectrum of quantum fluctuations, meaning fluctuations on all spatial scales are roughly equal in amplitude. This prediction is tested against the cosmic microwave background and found to be accurate to high precision. But nearly scale-invariant is not exactly scale-invariant, and there is some room for small deviations. If the primordial power spectrum had a slight excess of power on the scales that correspond to the sizes of the halos hosting the most massive early galaxies, it could allow more massive structures to form earlier. This is a concrete, testable modification. Different versions of this idea make specific predictions about the statistics of early galaxy masses that can be compared against Webb's growing catalogue. So far, the modifications required to explain the most extreme objects tend to push against constraints from the cosmic microwave background. The same enhancement that would help produce early massive galaxies also tends to predict signals in the microwave background that have not been observed. Threading this needle without violating existing constraints is technically difficult. Another theoretically motivated approach involves reconsidering the role of cosmic rays and magnetic fields in early galaxy formation. These components are often simplified or omitted in the largest cosmological simulations because they are computationally expensive to model. But in dense, rapidly star-forming environments like the ones Webb is observing, cosmic rays from supernova remnants can provide pressure support that changes how gas collapses and cools. Magnetic fields can similarly affect the fragmentation of gas clouds into individual stars. In principle, including these effects properly could change the predicted star formation efficiency. This is an active area of investigation, but the consensus is that while these effects are important for getting the details right, they are unlikely to produce the large factor of 10 discrepancies in galaxy number counts that Webb is finding. Perhaps the most intellectually honest position one can take in this situation is to acknowledge that we are almost certainly looking at a combination of effects. Some of the discrepancy may be explained by observational selection effects. Very bright, very massive early galaxies are the easiest ones for Webb to detect. If the true population of early galaxies is dominated by many more smaller, fainter galaxies that Webb is missing, then comparing the few massive ones we detect against the full model prediction is an apples to oranges exercise. Accounting properly for what Webb can and cannot see, a process called selection bias correction, is technically demanding and still being refined. Some of the discrepancy may be explained by physical effects that are underrepresented in current simulations, and some of it may genuinely require new physics. Working out the relative contributions of these factors will take years of careful analysis, but the important point is that even if selection effects and simulation limitations explain part of the gap, they are unlikely to explain all of it. The most extreme early galaxies, the ones that are most clearly incompatible with the standard model, are also the ones where the observations are most robustly confirmed. They are not borderline detections. They are bright enough to be analyzed spectroscopically. Their redshifts are confirmed. Their stellar masses are estimated using multiple independent methods. And they are still too massive. It is worth pausing to consider the population 3 star problem in more detail, because it sits at the heart of so many of these issues, and because Webb may be on the verge of directly observing these hypothetical objects for the first time. Population. 3 stars are the theoretically predicted first generation of stars in the universe. They would have formed from pristine primordial gas containing only hydrogen, helium, and trace amounts of lithium, the 3 elements produced in the first few minutes after the Big Bang. Without any heavier elements to act as coolants, the gas clouds from which population 3 stars formed would have been unable to fragment into small pieces. Instead, they would have collapsed into very massive objects, potentially hundreds or even thousands of times the mass of our Sun. These hypothetical stars would have been extraordinarily luminous, burning blue-white at temperatures far exceeding those of ordinary stars today. Their lifetimes would have been extraordinarily short, on the order of a few million years, because massive stars exhaust their fuel quickly. When they died, they would have enriched the surrounding gas with the first heavy elements ever. Produced in stellar interiors, the existence of population 3 stars is one of the most robust predictions of standard cosmological theory. Their properties follow directly from the known physics of nuclear burning in hydrogen-helium gas, but they have never been directly observed. This is not surprising given how briefly they existed and how long ago their era occurred. Finding individual population 3 stars is extraordinarily difficult because even Webb can only resolve individual stars in the nearest galaxies. At the distances where population 3 stars existed, we would see only the integrated light of entire galaxies, not individual stars. But there are indirect signatures to look for. The spectrum of a galaxy dominated by population 3 stars would look very different from a galaxy dominated by ordinary stars. The extreme masses and temperatures of population 3 stars would produce intense ultraviolet and X-ray emission. They would ionize the surrounding gas in distinctive patterns. Certain emission lines in the spectrum, particularly lines associated with helium ionization and the absence of metals, would stand out as population 3 signatures. Some researchers have reported tantalizing spectral features in a few of Webb's early galaxy observations that could be consistent with a population 3 contribution. But these detections are tentative and the interpretation is debated. The spectral features can sometimes be mimicked by other sources such as extremely hot ordinary stars or active galactic nuclei. If Webb can eventually provide clear spectroscopic evidence for population 3 stars, it would be a historic discovery. It would fill one of the most important gaps in our observational understanding of cosmic chemical evolution and provide direct evidence for one of the most fundamental predictions of theoretical cosmology. The hunt for these primordial stellar giants is one of the most exciting ongoing programs in Webb's observational agenda. The black hole growth problem deserves additional attention because it connects the early galaxy anomalies to a completely separate set of puzzles in astrophysics. We know that supermassive black holes exist at the centers of virtually all massive galaxies. Our own Milky Way harbors one with a mass of about 4 million times that of the Sun, confirmed by observations of stars orbiting it in tight, fast paths. The galaxy Messier 87, famously photographed by the Event Horizon Telescope collaboration in 2019, contains a black hole with a mass of about 6.5 billion solar masses. These objects are accepted components of the galactic landscape. The question is how they got there. In the early universe, the first black holes would have formed from the collapses of the first massive stars. A population 3 star ending its life with a mass of several hundred solar masses would leave behind a stellar mass black hole. For that black hole to grow to billions of solar masses in a few hundred million years, something dramatic must have happened. Continuous accretion at the theoretical maximum rate, the Eddington limit, would allow a black hole to double its mass roughly every 30 million years. Starting from a few hundred solar masses, reaching 1 billion solar masses in 500 million years requires that the black hole accrete continuously at the Eddington limit for essentially its entire existence without ever slowing down. In practice, black holes go through active and inactive phases. Continuous maximum accretion over hundreds of millions of years is difficult to sustain. Webb has found quasars, actively accreting supermassive black holes, had redshifts corresponding to the universe being less than 1 billion years old. Some of these have estimated black hole masses of several hundred million to several billion solar masses. Explaining how these objects grew so fast is genuinely puzzling. Proposed solutions include the formation of massive black hole seeds directly from collapsing gas clouds rather than from stellar remnants. Temporarily, super Eddington accretion where radiation somehow fails to halt the infall of gas, or the rapid successive merging of many smaller black holes. Each of these proposals has theoretical support and practical difficulties. The connection to the early galaxy problem is direct. In some scenarios, the rapid growth of supermassive black holes in the early universe and the rapid assembly of stellar mass in early galaxies are two aspects of the same underlying process. Both phenomena require matter to organize itself faster than the standard model predicts. Whether the solution to one problem is the same as the solution to the other, or whether they have different causes, is an open question that Webb's ongoing observations are actively investigating. The concept of cosmic noon is another lens through which to appreciate Webb's findings. Cosmic noon refers to the epoch approximately 2 to 3 billion years after the Big Bang, when the total rate of star formation across the observable universe reached its peak. Before cosmic noon, star formation was building up. After it, star formation declined as galaxies consumed their gas reserves and large-scale structure inhibited fresh gas infall. The decline in cosmic star formation rate from cosmic noon to the present is well documented by surveys conducted before Webb and is one of the most robust observational facts about the evolution of the universe. What Webb is revealing is that the build-up to cosmic noon was steeper and earlier than we thought. Some of the galaxies Webb finds in the first few hundred million years after the Big Bang appear to be undergoing intense star formation at rates that rival or exceed anything seen at cosmic noon. This is unexpected for an epoch that was supposed to be dominated by the slow accumulation of matter into the first small structures. The implication is that the rise toward cosmic noon began more steeply and earlier, which in turn implies that the matter distribution in the universe after the Big Bang was more concentrated in certain regions than standard inflation predicts, or that the physics of gas collapse and cooling in the early universe was different in ways that enabled more rapid star formation. Observationally, reconstructing the cosmic star formation history at very high redshifts is technically challenging. Surveys must correct for the fact that dust absorbs ultraviolet and optical light from star-forming regions and re-emits it as infrared radiation. Webb's infrared capabilities allow it to see some of what was previously hidden behind dust, which is partly why its picture of early star formation is different from what Hubble-based surveys suggested. Adding the dust-obscured galaxies detected by Webb's mid-infrared instrument to the count of already anomalously active early galaxies makes the discrepancy with standard models even larger. Every time astronomers think they have accounted for all the ways in which Webb's early universe differs from predictions, another observation adds to the discrepancy. This consistent trend, each new observational angle making the anomalies look more rather than less significant, is what is keeping the tension alive in the scientific literature. There is a deep philosophical point embedded in all of this that is worth making explicit. Science is not a collection of facts. It is a collection of models, each model an attempt to summarize an enormous amount of data into a compact description that makes testable predictions. Good models make predictions that are specific enough to be falsified. The Lambda-CDM model is an excellent example of this. It makes very specific predictions about the properties of the cosmic microwave background, the abundance of light elements, the clustering of galaxies, and the formation history of cosmic structure. These predictions have been tested with extraordinary precision over many decades, and in most cases they have passed with flying colors. But a model that passes many tests can still fail on others. Newtonian gravity passed centuries of tests and made extraordinarily precise predictions about planetary orbits, the precession of the equinoxes, and the tides. And yet it predicted something slightly wrong about the orbit of Mercury, and it had nothing to say about light bending around the sun. General relativity explained both. Newtonian gravity was not wrong in the sense of being useless. It remains the tool engineers and physicists use whenever relativistic effects are negligible. But it was incomplete. It was an approximation to something deeper. Lambda-CDM may be in a similar position. It may be an extraordinarily good approximation to the true behavior of the universe on the scales and epochs where it has been tested, but an approximation that breaks down in the extreme conditions of the very early universe. The question is what it breaks down into. What is the deeper framework that reduces to Lambda-CDM in the situations where Lambda-CDM works but that correctly predicts the early galaxies that Lambda-CDM cannot explain? Answering that question is now one of the central challenges of theoretical cosmology. It is a challenge being met with new computational tools, new theoretical frameworks, and new observational data. The answer, when it comes, will represent the next major advance in our understanding of the cosmos. Consider for a moment the chain of reasoning that allows us to make any of these statements with confidence. We detect light from distant galaxies. We measure the wavelengths of specific emission and absorption lines in that light. We know from laboratory physics what wavelengths those lines should have. We calculate how much the wavelengths have shifted. We use the physics of an expanding universe to translate that shift into a distance and a look-back time. We then calculate how massive those galaxies were using models of how stars of different types contribute to a galaxy's total luminosity. We compare those masses to what our simulations of structure formation predict should exist at that cosmic time. Every step in this chain involves physical principles that have been independently verified in other contexts. The physics of spectral lines comes from quantum mechanics, one of the most precisely tested theories in science. The physics of cosmic expansion comes from general relativity, another extraordinarily well-tested framework. The models of stellar populations draw on stellar physics that has been developed and tested across a century of observations. The N-body simulations of structure formation incorporate gravitational dynamics verified to high precision. When the end result of this chain of reasoning is a number that does not match the prediction, the discrepancy is not easily dismissed. It requires a revision somewhere in the chain. The most conservative revision would be to our models of stellar populations. If our estimates of how stars of different ages and compositions contribute to a galaxy's total luminosity are systematically off in the early universe, we might be overestimating the stellar masses of early galaxies. This is a real possibility, and researchers are working to constrain it. But the level of systematic error required to explain the full discrepancy is larger than current estimates of the uncertainty in stellar population models. The most extreme early galaxies cannot be explained away by plausible revisions to stellar population models alone. The next most conservative revision would be to the detailed physics of structure, formation within the Lambda-CDM framework, such as the efficiency of star formation or the behavior of baryonic feedback. These revisions are also actively explored. But, as we have discussed, the star formation efficiencies implied by some of Webb's observations exceed what the known physics of stellar feedback can easily accommodate. More radical revisions to dark matter properties, to the nature of dark energy, to the inflationary scenario, or to the fundamental picture of cosmic beginnings, are less conservative but cannot be ruled out. The history of science suggests that when observations consistently point in a direction that conservative revisions cannot easily accommodate, the more radical revisions are sometimes the correct ones. Webb is not the only instrument contributing to the growing pressure on standard cosmological models. The Hubble tension, as we discussed earlier, is measured entirely independently using local distance measurements and early universe physics. The fact that it disagrees at the 5 sigma level suggests that something is wrong in our understanding of either the local universe, the early universe, or the physics connecting them. Several proposals for resolving the Hubble tension involve modifications to the early universe that could also affect galaxy formation, suggesting a possible connection to Webb's findings. Large-scale structure surveys, which map the positions and redshifts of millions of galaxies, have also found some tensions with Lambda-CDM predictions in the statistics of galaxy clustering. The amplitude of matter fluctuations inferred from cosmic microwave background data does not match perfectly with the amplitude inferred from direct measurements of large-scale structure, a discrepancy sometimes called the sigma-8 tension. Like the Hubble tension, this is a statistically significant but not yet overwhelming disagreement that hints at something missing from our framework. Gravitational wave observations are adding a new dimension to this picture. The detection of gravitational wave backgrounds by pulsar timing arrays, announced in 2023 by multiple independent collaborations, suggests a stochastic background of gravitational waves permeating the cosmos. The properties of this background are consistent with, but not uniquely explained by, gravitational waves produced by the mergers of supermassive black holes throughout cosmic history. Interestingly, the amplitude of the background appears somewhat larger than the simplest predictions from models of supermassive black hole mergers calibrated to the observed galaxy merger rate. This could be another hint that massive black holes and their host galaxies assembled faster than models predict. Consistent with Webb's findings, what we are witnessing, across multiple independent observational probes, is the emergence of a coherent picture of anomalies. The early universe appears to have been more productive and more complex than we expected. Supermassive black holes grew faster than expected. Galaxies assembled earlier and more efficiently than expected. Chemical enrichment happened faster than expected. And in the local universe, the expansion rate appears to be faster than what early universe physics predicts. None of these anomalies individually demands a revolution in cosmology. Each could, in principle, be explained by a relatively modest modification of the standard model. But the fact that they all point in the same direction, toward a universe that organized itself faster and more efficiently than Lambda-CDM predicts, suggests that a single underlying explanation might be waiting to be found. Identifying that explanation is one of the most important open problems in physics today. Webb will continue observing for potentially decades. Its schedule already extends through the late 2030s, assuming the spacecraft and instruments remain operational, and early estimates suggest it may be able to operate for well over 20 years given the fuel efficiency of its launch insertion. The dataset it will accumulate over that time will be far larger than what we currently have. Statistical uncertainties that are now limiting our conclusions will shrink. The significance of the early galaxy anomalies will either grow or diminish as the dataset expands. New types of early galaxies may be discovered. The first direct detection of population 3 stellar signatures may be achieved. The epoch of reionization will be mapped in greater detail. The relationship between galaxy mass and black hole mass across cosmic time will be charted more precisely. Each of these advances will constrain the space of possible explanations and guide theoretical work toward more specific and testable models. The interaction between theory and observation in cosmology is always iterative. Observations motivate new theories. New theories make new predictions. New observations test those predictions. The cycle repeats, each iteration moving our understanding closer to the truth. We are currently at an early and exciting point in this cycle. Webb's first few years of observations have generated the anomalies. The theoretical response is now building, with research groups around the world developing new models aimed at explaining what Webb has found. The next phase of observations will test those models. If the next decade of Webb data continues to show the same anomalies, and if improved simulations still cannot reproduce them, the pressure for a more fundamental revision of our cosmological framework will become very difficult to resist. What would it mean to revise the cosmological framework? It could mean discovering new properties of dark matter. Perhaps dark matter is not cold but self-interacting, meaning dark matter particles occasionally scatter off each other in ways that change how dark matter halos form and evolve. Self-interacting dark matter models have been proposed to solve several puzzles about dark matter halo structure on galactic scales, and they might also affect early structure formation. It could mean discovering that dark energy is dynamic, evolving over cosmic history in ways that affected the early universe's expansion differently than the standard cosmological constant predicts. It could mean discovering that inflation was not as simple as the most basic single-field models suggest, perhaps involving multiple fields or non-standard dynamics that produced a different primordial power spectrum. Or it could mean something more radical, discovering that the Big Bang was not the beginning, that the universe has a history extending before it, and that the structures Webb is finding in the earliest observable epoch are not as young as they appear in our current chronology. Any of these discoveries would be major. Any would change how we think about where we came from and what the universe fundamentally is. The history of cosmology suggests that when observations force a revision of the framework, what emerges from that revision is always more surprising, more fascinating, and more accurate than what came before. Newton gave us a universe governed by universal gravity. Einstein revealed that gravity was the curvature of space-time. Hubble showed that space-time was expanding. Penzias and Wilson found the fossil glow of the Big Bang. Perlmutter, Schmidt, and Rees discovered that the expansion is accelerating. Each of these steps felt like the final picture was finally coming into focus, and each of them eventually revealed new mysteries that the previous picture had not anticipated. Webb is almost certainly showing us the beginning of another such step. What the next picture looks like, we do not yet know. But the outline is beginning to emerge from the data. A universe that organized itself faster than we expected. A universe whose earliest epochs are stranger and richer than our models predicted. A universe that, the better we observe it, keeps surprising us with its complexity. That is the most honest summary of where cosmological science stands right now. The instruments have never been better. The theoretical frameworks have never been more precisely tested. And the data being returned from the frontiers of observation has never been more unexpected. In the history of science, this combination has always preceded a breakthrough. We are waiting for that breakthrough. We are collecting the data that will make it possible. And we are living at the remarkable moment when the instruments of human curiosity are powerful enough to detect the structures of the universe's infancy and find, in those structures, evidence that our understanding is still incomplete. That incompleteness is not a failure, it is the frontier. And the frontier, as it has always been, is where the most important work is being done. If you found this exploration of one of the deepest open questions in modern science compelling, consider subscribing to stay connected as the story develops. Webb will keep sending data. Theorists will keep refining their models, and the universe will keep revealing itself, one ancient photon at a time. There is another dimension to this story that deserves careful attention: the human infrastructure that makes this science possible, and the sociology of how scientific communities respond when their frameworks are challenged. Science is often described as a self-correcting process, and this is true. But self-correction does not happen automatically or painlessly. It requires scientists who are willing to be wrong, willing to publish findings that challenge established consensus, and willing to engage seriously with anomalies rather than explaining them away. The early galaxy anomalies have been reported in peer-reviewed journals, but they have also faced significant skepticism from scientists who believe the Standard Model's track record justifies caution before declaring a crisis. This skepticism is not anti-scientific. It is appropriate. Premature declarations of paradigm shifts have a way of not surviving contact with additional data. The history of science includes many apparent anomalies that dissolved when methods improved, but there is also a risk in the other direction. If an anomaly is real and persistent, and the response of the scientific community is to repeatedly explain it away through ever more elaborate auxiliary hypotheses, progress is delayed. The history of science also includes cases where anomalies that should have prompted faster revision were resisted for too long. The eventual acceptance of continental drift, initially dismissed and then gradually vindicated, is a famous example. The lesson is that neither premature revolution nor excessive conservatism serves the long-term interests of science. The cosmological community appears to be navigating this balance thoughtfully with respect to Webb's findings. The anomalies are being reported openly and discussed seriously. Systematic errors are being investigated carefully. Theoretical alternatives are being developed and tested against data. The conversation is happening in the literature and at conferences with appropriate acknowledgement of what is established and what remains uncertain. This is science working as intended. One of the more fascinating aspects of the current situation is how it is reshaping the research priorities of the theoretical community. Before Webb, the most pressing theoretical questions in galaxy formation and evolution were largely focused on understanding galaxies in the nearby universe. Why do some galaxies stop forming stars while others continue? How do the properties of galaxies correlate with the dark matter halos they inhabit? What is the role of supermassive black holes in regulating galaxy evolution? These remain important questions. But Webb has introduced an urgent new frontier, understanding the first billion years of cosmic structure formation in detail, and doing so in a way that resolves the tension between theory and observation. Research groups that previously focused on the local universe are pivoting toward early universe problems. New collaborations are forming between observers who collect Webb data and theorists who run structure formation simulations. Proposals for new observational programs are being designed specifically to address the questions Webb has raised. The scientific community is reorganizing around the problem, which is exactly what should happen when a major telescope reveals unexpected features in a regime that was previously poorly constrained. The interplay between observation and computation is particularly interesting to watch. These simulations have reproduced many properties of the observed galaxy population with impressive fidelity, but they were primarily calibrated to match the properties of galaxies in the nearby universe, where observational data was most abundant before Webb. Their predictions for the very early universe, the regime Webb is now probing, are extrapolations into territory where little data existed to constrain them, and those extrapolations, it turns out, significantly underestimated what Webb would find. Next-generation simulations are being developed to do better. These include the Flamingo project, among others, which incorporates improved treatment of stellar feedback and other physical processes relevant to early galaxy formation. These simulations are beginning to produce early galaxy populations that are somewhat closer to what Webb observes, but the most extreme objects still resist explanation. The simulations can approach the observations by making choices about how physical processes work that are not independently confirmed. In other words, they can be tuned to match, but the tuning required is not obviously physically motivated. This is an unsatisfying situation for theorists who want models that work because they correctly describe the physics, not just models that match the data by having the right adjustable parameters. The ongoing development of better simulations is one of the most computationally demanding challenges in modern astrophysics. Simulating the early universe with sufficient resolution to capture the formation of individual star-forming regions, while simultaneously modeling volumes large enough to be statistically representative, requires computational resources that are only just becoming available. The next generation of supercomputers coming online in the mid-2020s will make it possible to run simulations that were previously too expensive. This computational frontier will be essential for determining whether the Lambda-CDM framework, with appropriately refined baryonic physics, can match what Webb is observing, or whether more fundamental modifications are needed. The connection between Webb's discoveries and the broader project of understanding cosmic evolution extends to questions about the reionization epoch in considerable detail. Reionization is one of the last great phase transitions in the history of the universe. After the cosmic microwave background was released about 380,000 years after the Big Bang, the universe entered the Dark Ages, a period during which there were no light sources and the hydrogen gas pervading the cosmos was neutral. This neutral hydrogen absorbed ultraviolet photons efficiently, making the universe opaque to that radiation. The Dark Ages lasted until the first stars and galaxies produced enough ultraviolet light to ionize the surrounding hydrogen, gradually clearing the cosmic fog over a period of several 100 million years. By about 1 billion years after the Big Bang, reionization was essentially complete and the universe had become transparent to ultraviolet radiation. The details of how reionization proceeded depend critically on the properties of the first galaxies. How many of them were there? How much ultraviolet radiation did they produce per unit of stellar mass? How efficiently did that radiation escape from the galaxies into the surrounding intergalactic medium? These are called the escape fraction of ionizing photons. Measuring the escape fraction of early galaxies is technically difficult because most of the relevant radiation has been absorbed by the time it reaches us. But indirect measurements using the properties of the intergalactic medium suggest that early galaxies had higher escape fractions than typical galaxies today, possibly because they were more compact and less dusty. If the early galaxies Webb is finding were forming stars as rapidly and efficiently as the observations suggest, and if they had relatively high escape fractions for ionizing radiation, they could have reionized the universe faster than standard models predict. This would shift the reionization timeline earlier and alter the properties of the intergalactic medium at high redshift. Future observations with Webb and with the Square Kilometre Array will be able to test this by mapping the distribution of neutral hydrogen at different redshifts and comparing the timing and spatial structure of reionization against theoretical predictions. The epoch of reionization is also connected to the formation of the first generation of quasars. Quasars are the most luminous objects in the universe, powered by supermassive black holes accreting matter at close to the Eddington limit. The most distant known quasars are already in place at redshifts greater than 7, corresponding to less than 700 million years after the Big Bang. These objects produce enormous amounts of ionizing radiation that can clear the surrounding intergalactic medium. Understanding how these quasars formed and grew so quickly connects directly to the black hole growth problem discussed earlier, and it also connects to the galaxy formation problem through the coevolution of supermassive black holes and their host galaxies. Big has already discovered new quasars at very high redshifts and is providing new insights into their host galaxies, which were previously undetectable. The host galaxies of the most distant known quasars turn out to be themselves anomalously massive for their epoch, adding another layer to the early massive object problem. Looking forward across the next decade and beyond, the scientific community's strategy for resolving the questions raised by Webb is becoming clearer. It has three main components. The first is to continue and expand the observational program. Webb will continue accumulating deep field data, building up statistical samples of early galaxies large enough to characterize their population properties with high confidence. Follow-up, spectroscopic observations of the most anomalous candidates will confirm or refute their redshifts and provide more detailed physical characterization. Ground-based extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, will provide complementary spectroscopic capabilities at visible and near-infrared wavelengths. The square-kilometre array will map neutral hydrogen across the epoch of reionization. These combined observational programs will dramatically expand our view of the early universe over the next 10 to 15 years. The second component is to improve theoretical and computational models. The next generation of cosmological simulations will incorporate more realistic physical processes, higher resolution, and larger volumes. New theoretical frameworks for dark matter and dark energy will be developed and tested. Alternative cosmological models that predict different early structure formation will be evaluated against the growing observational dataset. The goal is to narrow down the space of viable theories by making their predictions as specific and testable as possible, then comparing those predictions against data. The third component is to develop new observational probes that provide independent tests of cosmological models. Gravitational wave astronomy, 21-centimeter radio observations of the cosmic dark ages, and next-generation cosmic microwave background experiments will each provide information about the early universe that complements what Webb can provide. Multi-messenger approaches combining these different observational windows will offer the most complete picture of the early universe's history. The convergence of all these programs over the next decade or two is expected to resolve the current tensions either by finding explanations within the Lambda-CDM framework or by identifying which aspects of the framework need to be modified. Either outcome will represent a major advance in our understanding. There is something almost vertiginous about this scientific moment if you pause to appreciate it fully. We are looking at light that has been traveling since the universe was less than 3% of its current age. We are using that light to count galaxies that formed within a few 100 million years of the Big Bang. We are measuring the wavelengths of specific spectral lines in that light and inferring from those measurements the masses, compositions, star formation rates, and black hole activities of objects that no longer exist in the forms we see them. We are comparing those measurements against theoretical predictions derived from equations describing the behavior of quantum fields in the first trillionth of a second after the Big Bang. And we are finding, in that comparison, specific quantitative discrepancies that tell us our theory is incomplete. The fact that any of this is possible is itself one of the most remarkable achievements in human intellectual history. Physics and mathematics have given us the tools to reach back nearly to the beginning of time with quantitative precision. The universe turns out to be comprehensible. Its behavior at all scales and all epochs, from quantum mechanics in the early cosmos to the expansion of space across billions of light years, appears to follow mathematical laws that we can discover by observation and test by prediction. This comprehensibility is not guaranteed. There is no logical reason why the universe should be comprehensible to beings who evolved on a small planet to navigate a world of moderate complexity. The fact that it is, and the fact that the same mathematical structures that govern subatomic particles also govern the large-scale dynamics of the cosmos, is one of the deepest mysteries in all of science. Physicists have called it the unreasonable effectiveness of mathematics in describing the natural world. Webb is showing us that our current mathematical description, while extraordinarily successful, is not yet complete. The next chapter of cosmology will involve discovering what needs to be added to or modified in that description. It will involve new ideas, new instruments, new observations, and new theories. It will take time. Science at the frontier always does. But the trajectory is clear. We are closer to a complete understanding of cosmic origins than any previous generation of scientists. The tools at our disposal are more powerful than any that came before. And the universe, for all its enormity and complexity, is willing to be understood. It announces its properties through light and gravity and the patterns of matter, and we are learning to read those announcements with increasing precision. The early galaxies that Webb is finding in the universe's infancy are among the most ancient messages the cosmos has sent us. They were written 13 billion years ago in the language of photons and spectra, and they have been traveling to us ever since. Webb has given us the receiver capable of reading them. What they are telling us in quantitative detail is that the universe began more dynamically than we thought, organized itself more rapidly than we expected, and produced complexity in its first moments that our best theories are still struggling to explain. Understanding those messages fully will take the efforts of the next generation of scientists, instruments and ideas, but understanding them is within reach. The universe has secrets, but it is not keeping them forever. Science, that most extraordinary of human enterprises, is in the process of uncovering them, and the James Webb Space Telescope, floating in the cold quiet of space 1.5 million kilometers from Earth, is one of the finest instruments our civilization has ever produced for that purpose. The work continues. The early universe is still giving up its secrets, and every ancient photon that arrives at Webb's detectors is another sentence in the story of how everything began. It is worth spending some time on what we have learned about dark matter, specifically from the early universe observations, because dark matter is at the center of so many of the puzzles Webb is highlighting, and yet it remains one of the most mysterious components of the cosmos. Dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who noticed that galaxies in the Coma galaxy cluster were moving too fast to be held together by the gravitational pull of their visible matter alone. He proposed that there must be additional invisible mass providing the extra gravitational glue. The idea was largely ignored for decades. It was revived in the 1970s, when Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found that stars at the outer edges of galaxies were orbiting just as fast as stars closer to the center, when physics predicted they should be orbiting more slowly if the galaxy's mass was concentrated in its visible stellar disk. The only way to explain these flat rotation curves was to invoke a large halo of invisible matter surrounding the visible galaxy and extending far beyond it. Today, the evidence for dark matter is overwhelming and comes from multiple independent sources: galaxy rotation curves, the gravitational lensing of background light by galaxy clusters, the dynamics of galaxies within clusters, the large-scale structure of the universe and how it evolved, the acoustic peaks of the cosmic microwave background. All of these observations, interpreted within the framework of general relativity, require the existence of roughly 5 times as much dark matter as ordinary visible matter. But despite this overwhelming indirect evidence, no experiment has ever directly detected a dark matter particle. The leading theoretical candidates are weakly interacting massive particles, or WIMPs, which would have been produced in the hot early universe and would interact with ordinary matter through the weak nuclear force and gravity, but not through electromagnetism. WIMPs are attractive because their expected mass and interaction cross-section happen to produce roughly the right dark matter abundance through a mechanism called thermal freeze-out. But decades of increasingly sensitive experiments searching for WIMP interactions in underground laboratories, searching for WIMP annihilation signals in the centers of galaxies, and searching for WIMP production at particle accelerators, including the Large Hadron Collider, have come up empty. The most sensitive direct detection experiments have now ruled out most of the theoretically favored WIMP parameter space. This has led to increasing theoretical diversity in dark matter models. Alternatives now being taken seriously include axions, extremely light particles originally proposed to solve a different problem in particle physics, sterile neutrinos, hypothetical heavier cousins of the known neutrino species, primordial black holes that might have formed in the early universe before stars existed, and entirely novel categories of particles in dark sectors that have no counterpart in the standard model of particle physics. Different dark matter candidates predict subtly different behavior in the early universe, and it is possible in principle that Webb's observations of early galaxy formation could discriminate between some of these alternatives. For example, ultralight dark matter, sometimes called fuzzy dark matter, consists of particles so light that they have wavelengths comparable to the sizes of the smallest galaxies. This quantum mechanical behavior would suppress the formation of very small halos below a certain mass threshold. If the early anomalous galaxies Webb is finding exist in halos that are too massive to be affected by fuzzy dark matter, then fuzzy dark matter cannot explain their formation. But if the smallest galaxies in Webb's surveys turn out to be different from what cold dark matter predicts, fuzzy dark matter might offer an explanation. These discriminations require precise statistical measurements across a range of galaxy masses and redshifts, exactly the kind of data Webb is uniquely positioned to provide. The same logic applies to self-interacting dark matter, which predicts that dark matter halos have cores of nearly constant density at their centers rather than the density cusps predicted by cold dark matter. This prediction can be tested by studying the dynamics of stars and gas in the centers of galaxies at various cosmic epochs. Webb's ability to observe early galaxies at high redshift could, in principle, reveal whether their central dark matter distributions are more consistent with cores or cusps. Although this measurement is technically extremely challenging, the point is that the early galaxy anomalies are not isolated curiosities. They connect to deep questions about the fundamental nature of dark matter that are also being investigated from multiple other directions. Progress in understanding the early universe and progress in understanding dark matter are deeply intertwined. Similarly, the early galaxy anomalies connect to questions about dark energy that go beyond simply measuring how fast the universe is expanding. If dark energy is truly a cosmological constant with a fixed value, then its influence on the early universe was negligible. Dark energy only becomes dynamically important when the universe is old and large enough for its constant energy density to compete with the diluting density of matter. In the early universe, when matter density was enormous, dark energy would have been irrelevant. But if dark energy is not constant, if it is a field that evolves over time, its behavior in the early universe could have been different from what we assume. Some models of early dark energy posit that there was an additional component of energy density in the early universe that decays away, boosting the early expansion rate and potentially resolving the Hubble tension. These models also affect the growth of structure and could change the predicted properties of early galaxies. Testing early dark energy models against Webb's galaxy observations is technically challenging because early dark energy affects galaxy formation through the Hubble expansion rate and the growth factor of perturbations in ways that are degenerate with other uncertainties. But as theoretical models become more specific and observational datasets become larger, these degeneracies can be broken and meaningful constraints can be placed on early dark energy parameters. All of this points toward a future in which the different strands of observational and theoretical cosmology, galaxy formation, dark matter direct detection, gravitational wave astronomy, cosmic microwave background measurements and large-scale structure surveys will be woven together into an increasingly precise picture of the universe's history and content. The anomalies that Webb is highlighting today are likely to be among the most important clues in assembling that picture. There is a broader cultural context for these discoveries that is worth acknowledging. We live at an extraordinary moment in human history when the tools of scientific observation have advanced to the point where we can directly probe the universe's infancy. Previous generations of scientists could theorize about the early universe, could extract indirect information from the cosmic microwave background and the abundance of light elements. But they could not directly observe what the first galaxies looked like. Webb has changed that. For the first time in human history, we are seeing ancient cosmic structures with enough detail to test specific quantitative predictions of specific cosmological models. This is a turning point in cosmology, comparable to the transition from theoretical prediction to direct observation that occurred in other fields. Astronomers predicted the existence of black holes from the mathematics of general relativity, but it took decades before we had instruments sensitive enough to detect them directly. We now have images of black hole shadows and gravitational wave signals from merging black holes. Particle physicists predicted the existence of the Higgs boson from the mathematics of the Standard Model decades before the Large Hadron Collider confirmed its existence. Direct observation changes the nature of a scientific question. What was previously a theoretical possibility becomes a quantitatively characterized physical reality that must be accounted for. Webb is doing exactly this for the early universe. What was previously accessible only through theoretical modeling and indirect inference is now directly observable. And what we observe is not quite what we expected. The science is hard, the anomalies are real, and the resolution requires serious intellectual effort. But the data is there. It is being collected, and it is of the quality needed to discriminate between competing theoretical explanations. The scientists working on these problems are some of the most talented and dedicated researchers in the world. They spend years developing the technical expertise needed to build instruments like Webb, to reduce and analyze the data it returns, and to develop the theoretical frameworks needed to interpret what it finds. The graduate students entering cosmology today will likely be the ones who work out the meaning of Webb's discoveries and build the theoretical framework that resolves the tensions we are now identifying. They are entering the field at one of the most exciting moments in its history. What is particularly heartening about the scientific response to Webb's findings is its openness. The anomalies are not being suppressed or minimized. They are being reported publicly, discussed at conferences, debated in the literature, and investigated with additional observations. This is science functioning as it should, as a self-correcting, evidence-driven enterprise in which the truth eventually wins out against prior assumptions, no matter how well established those assumptions appeared. The universe does not care what we expect it to do. It follows its own laws, produces its own structures, and evolves in its own way. Our job, as scientists and as curious beings, is to observe it carefully enough to discover what those laws actually are. Webb is giving us an unprecedented view of how the universe exercised those laws in its earliest epochs. The view is surprising, the surprises are informative, and the information is leading us toward a better understanding of everything. Every great telescope in history has revealed something unexpected. Galileo turned his telescope on Jupiter and found moons orbiting it, destroying the idea that all celestial bodies orbit the Earth. Herschel mapped the Milky Way and discovered it had a structure. Hubble proved that the nebulae were other galaxies, expanding the known universe by a factor of trillions. Penzias and Wilson detected the cosmic microwave background, confirming the Big Bang. The Hubble Space Telescope resolved individual stars in nearby galaxies with unprecedented clarity and deepened our understanding of cosmic distance and the history of star formation. And now Webb is showing us the first galaxies in unprecedented detail and finding that they are not what our best theories predicted. This pattern of telescopes revealing unexpected features that require revision of our understanding is not a sign of scientific failure. It is science's greatest strength. Each revision brings us closer to the truth. Each unexpected discovery teaches us something we could not have learned any other way. The universe is more complex and more interesting than any theory we have yet invented to describe it, and telescopes are the instruments by which we discover how. Webb is the current frontier of that discovery. Its observations of the early universe are the most detailed and quantitatively precise we have ever obtained from the first few 100 million years of cosmic history, and they are telling us, with increasing confidence, that our understanding of that epoch needs to deepen. Whether the required deepening is a refinement of existing models or a more fundamental revision remains to be determined, but the determination is underway. The data is flowing, the analysis is ongoing, and the answer, when it comes, will be worth the effort. One final dimension of this story that deserves attention is what the Webb anomalies tell us about the nature of scientific knowledge itself, and why the current moment in cosmology is so genuinely unusual. Most of the time, science advances through what the philosopher Thomas Kuhn called normal science, the careful, detailed working out of implications within an established framework. Scientists know roughly what they expect to find and are working out the details. Anomalies are encountered, but they are typically explained as measurement errors, or resolved through minor adjustments to the framework, or set aside temporarily as problems that will be solved eventually. Normal science is productive and important, but it is not transformative. What Kuhn called scientific revolutions are different. They occur when anomalies accumulate to the point where the existing framework can no longer accommodate them through minor adjustments. When theorists begin proposing radically different frameworks, when debates become fundamental rather than technical, and when eventually the scientific community as a whole undergoes a shift in worldview. These events are rare. They include the Copernican revolution that replaced the Earth-centered model of the solar system with the Sun-centered one, the Newtonian synthesis that unified terrestrial and celestial mechanics, the Einsteinian revolution that replaced absolute space and time with relative space-time, and the quantum revolution that replaced continuous classical physics with discrete probabilistic quantum mechanics. We are not yet at a scientific revolution in cosmology. The anomalies from Webb are significant and persistent, but they are not yet so overwhelming that the Lambda-CDM framework has been abandoned. The framework still explains the vast majority of cosmological observations, but we may be in the early stages of what could eventually become a revolutionary moment if the anomalies continue to accumulate and if no satisfactory explanation within the existing framework is found. This possibility should be approached with appropriate humility and appropriate excitement. Humility because the history of science includes many apparent anomalies that dissolved with better data or better analysis. Excitement because the history of science also includes genuine revolutions, and we may be witnessing the early signs of one. The scientists working at the frontier of this problem are exercising both of these qualities simultaneously. They are being rigorous about quantifying uncertainties, careful about claiming more than the data support, and open to the possibility that whatever explanation emerges may require fundamental new ideas. That combination of rigor and openness is the defining characteristic of good science at the frontier, and it is on full display in the scientific community's response to what Webb is finding. The James Webb Space Telescope was built by thousands of engineers, scientists, and technicians over more than 2 decades at a cost that represents one of the largest peacetime investments in pure science that any government has ever made. It was launched on Christmas Day of 2021, deployed with extraordinary precision, cooled to its operating temperature, calibrated over several months, and then set to work observing the cosmos. In its first years of operation, it has produced more than 1,000 scientific papers and has already transformed our understanding of galaxy formation and evolution. Investment has been justified many times over, not just in scientific terms, but in human terms. The universe that Webb is revealing is stranger and more fascinating than the one we thought we understood. The early cosmos was more active, more productive, and more complex than our models predicted. The first galaxies were more massive, the first black holes grew faster, the chemical enrichment of the cosmos happened more quickly than our best theories allowed. These are not minor refinements. They are substantial discoveries about the history of everything that exists, including us. Every atom in your body was produced in a star. The timeline of when those atoms were made, in what kind of stars, and how they were distributed across the universe to eventually end up in the nebula that formed the solar system, is part of the cosmic history that Webb is now illuminating in unprecedented detail. The discovery that this history happened faster and more efficiently than we thought means that the ingredients for life may have been available in the universe earlier than we assumed. The possibility, still speculative, that life could have first arisen in the universe earlier in cosmic history than current models predict, is among the most profound implications of Webb's findings. We are stardust with telescopes, looking back at the stars that made us and finding that they formed faster and earlier and in greater numbers than we knew. The universe that produced us is more extraordinary than the one we thought we inhabited, and understanding it better with the tools and minds that the universe itself has produced through billions of years of stellar and biological evolution is the most human enterprise imaginable. That is where the science stands. That is what Webb is showing us. And that is why the coming years of cosmological research, as Webb continues to observe and new instruments come online and new theories are developed and tested, are likely to be among the most scientifically consequential in the history of our civilization. The early universe still has much to say. We are now, for the first time, equipped to listen.